My name is Miguel Morales. I work in Lawrence Livermore National Lab. I'm going to be talking about auxiliary field. I'm going to, 3/4 of the way, roughly of the 2 hours that we have assigned, I'm going to be describing sort of a bird's eye view of auxiliary field. And then Fiona is going to talk a little bit at the final half an hour about the tools and essentially how to go from, basically continue Anwar's talk into how to go from Pioneer and generate the input for QMC back. Sorry. Okay. So this is a brief overview. Essentially, this is the first time that we talk about AFQMC in any of our workshops. AFQMC is an orbital-based method, as I'm going to explain. It's new to QMC Pack. QMC Pack probably has, I'm going to guess, 15 years of history. AFQMC has been in there for maybe a year or two. And now we're finally at the point where it is production ready and we can actually advertise many of its features. Because we have never talked about it in the past, as opposed to all of the other talks that you're going to hear today, I'm going to give a little bit of detail, not a detailed description of the method, but a brief summary of all the main points so that maybe you can go back home with some idea of essentially what AFMC is. And I'm going to assume to some degree, or at the very least, I'm going to make reference to DMC consistently throughout the talk, and the idea would be to compare and contrast AFQMC with DMC. And hopefully, every time you have a material or a calculation that you want to do, hopefully we get to the point where you actually ask yourself which of the two methods is actually preferable for this particular calculation. And then I'm going to finalize with a brief overview of what's actually in QMC Pack, what is sort of the design principle of what's in the code, and features, and what's coming. And then we're going to switch to Pia, who again is going to talk about the tools. Okay, so you cannot see this, kind of meant for it to be that way. It's not to be seen right now. This is a list of papers I could think of yesterday when I was doing the talk. Of course, the list of references in AFMC is very large. You can probably do several dozen papers that are really relevant to the field, but this is just a couple of recent papers to pique your interest so that you can look at those when you go back home and start following the reference trail if you're interested.
This was a dumb question, but I was looking at the repo. What is your talk up there that we could?
Yeah, I have a different version.
Really?
Yeah.
Well, it might be the colors are quite different because
No, it's totally
it's
different.
the content,
What's the file name? Sorry.
day one AFQMC.
not this one.
Look in the main directory.
Oh no, that is Fion's second piece.
Oh, we might
So it
have
should
to
be in the
pull-
main directory, yeah. So
No?
if you go to the top of the repository where all the other talks are, there should be one called day1_AFQMC.
You might have to pull again.
Yeah, you may have to refresh because I put it in maybe an hour and a half ago. I'm sorry. And so the other thing is, I have something like 25 slides. So if I just speak quickly, I would have plenty of time. So if you have questions, you just want to, if you don't agree with me, which you want to have a discussion, I think we can accommodate that. And then when we get to the end, I might have to speed up a little bit, but I would be glad to answer questions and talk about things. So continuing, essentially this is just a couple of papers to pique your interest, and then you can start following the paper trail. So what is auxiliary field quantum Monte Carlo? So essentially, AFQMC is DMC, but done in a slightly different space. So instead of having electrons in real space that diffuse and whose distribution eventually follows the wave function in real space, we're basically not living in real space, we're living in orbital space. So which orbitals we work with is semi-irrelevant. The idea is that we have some set of single particle states. These single particle states define some fraction of the Hilbert space, and the projection of the wave function in this part of Hilbert space essentially defines the problem. We're going to have a lot of benefits and disadvantages when we do that, and I'm going to talk about those in a little bit. But from the high level, essentially looks identical to diffusion Monte Carlo. It's all the same elements. So you're going to have a wave function that's represented as some sort of average over some quantity. In the case of DMC, that quantity is coordinate space, so you have your tree-end space that defines your density. Your wave function, in our case, is going to be Slater determinant space. So we're going to have some sort of reference determinant and all possible rotations of that determinant within the basis set that we choose. And essentially, that's going to be what's going to define our trial wave function, our sort of ground state or whatever state we're interested in. And similar to DMC, we're going to employ a discrete stochastic representation of that wave function. So we're going to have walkers. Those walkers are going to evolve in time, and their collective, this average over time, is going to define a distribution that essentially is going to define our target many-body state. So we're going to have branching, load balancing, all of the same features that DMC has. The only problem is that the walker is not tree-end coordinates; it's going to be a matrix essentially. So we use the same basic idea of diffusion Monte Carlo, which is the imaginary time propagation of any trial wave function leads you to a well-defined eigenstate. Of course, the trial wave function has to be non-orthogonal with the whatever state you're interested in, but if we apply the propagator of the system for a long enough time, we're always going to reach some sort of target eigenstate, in most cases, the ground state. And we're going to use exactly the same idea as DMC, where we are going to break up this propagator, which is going to converge in the infinite imaginary time limit. We're going to choose some large enough number. We're going to break that number into small pieces, and we're going to basically iteratively apply this propagator to some state. And when we do it enough times, we're going to reach a sample. We're going to be able to sample the ground state identically to DMC. Again, the difference now is that whereas in DMC, this Hamiltonian is written in real space, where your interaction is 1 over r, for example, in Hilbert and in auxiliary field, it's going to be defined by the matrix elements of the Coulomb interaction between all the states in my basis set. So it's going to look different, but the purpose is exactly the same. And then properties are going to be calculated exactly as we do in diffusion Monte Carlo. We have 2 ways of calculating properties. We have the mixed distribution, or in DMC jargon it's called forward walking. In AFQMC it's called back propagation. It's essentially the same thing. You sample, and then you take pieces of the sample path to create your left and your right states. And so either the left-hand side is a trial wave function, that's a mixed distribution, or you actually propagate the trial wave function some amount of imaginary time, and you have a well-projected wave function on both sides. And I'm going to say a little bit more about that, but on general, it basically looks exactly the same. Okay, so I have a few slides where there's some math. It depends on where you are. This is a varied, there are probably multiple backgrounds, and it's pretty hard to give a complete and detailed introduction to auxiliary field in a situation like this. So I'm gonna, try to explain as much as I can, and please, if you have questions, or if I'm just saying things that nobody can understand, please let me know. So I'm just gonna set the setting for exactly what the space is and what is auxiliary field. So the first and the most important thing is what is the Walker representation? What is a Walker in auxiliary field? So we're going to be constrained. Typically, we do this in a canonical ensemble, so the number of electrons is fixed. We're going to have some total number of electrons, which gets split into some amount of up and down electrons. Typically, say alpha and beta, but essentially it means up and down. The first thing that you have to define is some sort of single particle space, single particle basis set. This can be essentially anything. The method is completely agnostic to what the single particle basis is. It can be plane waves in a solid, it can be Gaussians in a molecule, wavelets, it can be a traditional basis set like the ones that I mentioned. It can also be the solution of a mean field calculation, for example. You can take as your single particle basis set the Hartree-Fock states or some sort of DXT states. Essentially what you want is single particle states. There's a lot of choice here, and as I'm going to explain later, the code inside QMC back doesn't really know what this is. All of these calculations are done outside in the mean field code, like ISCF, for example. That's where you make all of the decisions about bases, electron positions, and things of that matter. And the auxiliary field code doesn't really care what your decisions are. So for some notation in some of the equations that follow, we have your usual creation and annihilation operators, which create or destroy an electron in the particular single particle basis set. We also have single particle orbital sets, which are now electronic orbitals, essentially. These are the states where the electrons live, and they, of course, are written in terms as an expansion of your states in your single particle basis set. M is always going to refer to how many single particle basis elements I have, how many elements I have in my single particle basis, and N is always going to refer to the number of electrons. So this, for example, defines some single particle state, which we typically characterize by some matrix because our Walker essentially is going to be fully characterized by the N single particle orbitals that the electrons are going to be occupying. And we typically write them on this way, where each column on this matrix represents the expansion of some single particle orbital in the basis of the single particle states. And of course, the actual Slater determinant is going to be defined by creation operators of these states on some vacuum.
Miguel, sorry, so if I understand well, so do you also take into consideration unoccupied orbitals or not?
There is no such a thing. So he asks, do we take into account unoccupied orbitals? Because we're working in non-orthogonal Slater space. Essentially, there's no such a thing as occupied or unoccupied. You just have n electron states that span some part of this Hilbert space. So the formulation of the method is in second quantization because we're working on a well-defined basis. Essentially, we turn our operator problem into linear algebra, which we love because class is awesome. So in real space, your Hamiltonian would look like this, where you have your kinetic energy operator, your whatever the external potential is. Typically would be something like Lubboch's NCSU potentials, for example, pseudo potentials. But essentially, it's somewhat irrelevant. And then you have your electron-electron interaction, which in general, it would be 1 over R, but you can take screen interactions. You can essentially put anything in there. It doesn't matter. Then once we define, given a single particle basis, like we defined before, we can turn this equation, this operator, essentially into second quantized notation, where now all the information of the Hamiltonian is encapsulated into two tensors. What I'm defining here as the Tij, which is the one-body part of the Hamiltonian. This one-body is simply the matrix element of this part of the Hamiltonian, of the one-body part of the Hamiltonian, with respect to any two elements in your single particle basis. And your two-body Hamiltonian, which would have this type of form, is the corresponding matrix element between every pair of single particle states. For those with a chemistry background, these are what the usual two-electron integrals. I used to use physics notation. I just realized after working at AFQMC that the chemists really are the ones who have this right. So this is a much better notation when I use it from now on. Anyway. So the whole point is that through these two tensors, we encapsulate the Hamiltonian essentially. As you can see, this is a fairly simple Hamiltonian. This is a very simple operator. You only have two indexes, so it's only an m squared. This is a beast. This is an n to the fourth object. So all of the complexity of the method, which is also similar to quantum chemistry methods, is essentially how you handle this beast. And all the efficiency, what can we do with the method, is ultimately limited by essentially how do we handle this thing. I'm going to come back to that in the next slide. So essentially, another important point, which I'm going to say here, is that in general, this has this structure. We can always rewrite this term into something that looks as perfect squares of a one-body operator, and this is going to be important. There are multiple ways of going from here to here. This is so the B's are one-body operators, and this is essentially, you can always rewrite this as something that has a one-body operator plus perfect squares of some rotated one-body operators. This is going to be very important in the next step. And this is completely generic. There are multiple ways of doing it, but you can always do it essentially. So how do we propagate walkers? As I said before, we have walkers. They represent the wave function when we propagate them for long enough time. The question is, how do we represent the exponent of minus tau h. And this is where AFQMC has its character, essentially. There are multiple ways to work on orbital spaces, and there are multiple ways of representing the propagator of the system. AFQMC is characterized by using the Hubbard-Stratanovich transformation. So before I go there, the one key point which somebody many years ago realized is that if you have a Slater determinant and you want to apply a one-body propagator, which in other words is the exponential of an operator that only has essentially one pair of C dagger C, if you apply that on a Slater determinant, you always get back another Slater determinant. So as long as we only use one-body propagators, the propagations remains closed in the space of Slater determinants. You're just jumping from one Slater determinant to the other. This is crucial and essentially the main point of most methods. And so another important thing is that once we have one-body propagation like this, all we need to do, and this takes some math, and I'm not going to say it here, but all it takes is essentially, these are now the matrices representing the Slater determinant. So you just need to apply the exponential of the matrix defining your one-body operator to the Slater matrix of the incoming Slater determinant, and that will produce the Slater determinant representation of your new state. So essentially, matrix multiplication allows us to do one-body propagation very efficiently. So if we could turn the propagator of the system into something that only contains one-body operators, we're basically done. And so the third point is, how do we do that? AFQMC uses what's called the Hubbard-Stratanovich transformation, which was, of course, invented by mathematicians many years ago. And the whole point is that you can write essentially it's Gaussian integration for operators. And you can show that you can take an operator, the propagator of a two-body operator, and it has to be the squared, perfect square of a one-body operator. So you have to complete the square. But essentially, you can rewrite it as an integral over fields. These are now scalar quantities over one-body operators. You get a Gaussian weight and a one-body propagator that couples now your field with your operator. And notice that because of this negative sign, it is actually carry over, and you actually have imaginary time propagation. Essentially, you don't propagate in real numbers anymore. You get a phase. This is going to be important in a few slides. But you can turn any two-body propagator into an integral over one-body ones. And so after that, all you need to do are the standard approximations that are also done in DMC. You do your breakup that I mentioned before. You take a long imaginary time and you break it up into small pieces. And then all you need to do is to come up with an approximation to this propagator for a small time. We use the usual Trotter approximation, also similar to DMC, where you have your one-body pieces on the ends, and you do it symmetrically so that it actually gives you the square convergence. And then you put in the expensive, complicated two-body piece in the middle. And after some math, which I'm not going to show here, you can show that by using this formula. Sorry, can I go the other way? One more, yeah. So by using this formula, into each one of these components independently, essentially, you can rewrite your full propagator as a product of propagators that contain an integral over a field, and now a propagator that's dependent on this field and has this form. And if you see, this compares to this form in just that the two-body operator has been replaced by this one-body operator that's coupled to this external field. This external field is sampled from a Gaussian distribution, so you can think of auxiliary field as essentially non-interacting systems propagating in time under a Gaussian external field, essentially. And the average over all of these fields is going to give you the ground state or some particular ideal state of the system. So if we know how to propagate non-interacting systems, we can essentially do auxiliary field. So here, I'm going to put these things here. They're not essential to the discussion, but they are relevant if you actually want to do auxiliary field calculations, and they come back a little bit later when we talk about the features in the code. So these are standard tricks. It's the same thing in diffusion Monte Carlo, where you have, if you do the calculation I would say naively, just in the simpler setting, you're going to get a large variance and things are not going to be quite as efficient. So you have to, in the same way, essentially, all of this was derived by Shiwei Shang some 15 years ago. He looked at what the way DMC was done, and he said, all of these things we can put in orbital space, and they have essentially a direct mirror. Mean field subtraction is the only one that's slightly different, and essentially, the idea is pretty simple. In your previous potential, in your previous formulation, you had just the sum of these squares. Essentially, you can always subtract any quantity to these fields, and the whole point is that all the stochasticity and all the variance and the noise in the calculation is going to come through the integrals of the fields. So if you can make the term that goes into that random part as small as possible, you're going to be able to reduce the noise and increase the efficiency. So essentially, all you do is you make an honest attempt at basically reducing the average of that quantity over your simulation. And the only real thing that you have in hand is essentially, if you have a try-wave function, you can see what the average value of that number is given the try-wave function, and you just subtract that zero. So you reset the zero each term. And so a little bit of math just shows that this just it reduces the magnitude of the two-body term and gives you, as a result, essentially a one-body piece that you can just stick on H1 and keep going as you were before. So when we do this, the algorithm doesn't change. You just need to redefine what H1 is to include these two pieces, and you need to redefine your two-body operator, essentially. The other part that's important is important sampling and force bias. This is identical to diffusion Monte Carlo. It's the idea that when we're sampling, if we sample the space, if we sample these fields completely blind, in a completely uniform distribution, we're going to be going most of the time through space where there is no meaning, where there's no essentially space that is not important. So the best way to sample space is to bias the sampling towards places where we know we have some idea that there is importance, and usually the try-wave function gives us a very good, essentially, sampling bias.
Yes. And can AFQMC suffer as badly from undersampling as DMC can if you make a trial function that's too tight, and you put zeros in a lot of places where you actually sample?
So the wave function has to be normalized, of course, so the wave will be somewhere. If the trial wave function is bad and it's really, let's say that you want to sample a state and you use as a trial as a wave function where the wave is completely in a different part of Hilbert space, then yes, of course. Typically, the whole point is that you can look at fluctuations of the simulation and get some idea of what the quality of the trial wave function is. And as we will see later, there's no free lunch. You have to get either you know that the trial wave function is good, or you have to at least have a path towards checking what the quality of the wave function is in order to gain some confidence. But this is identical to DMC.
There were known cases where it works. Like if you're looking at DMC, you're looking at ground states versus excited states, you know that you're going to have some undersampling problems if you try one, the other, and things like that.
Right. So it's quite different to DMC in that respect. So he's asking what about ground state and excited states, where you know that due to the nodal surface, you won't be sampling the same space. AFQMC, the constraint, as I'm going to show, it's identical in spirit to real space, but it's done in a completely different space. So, for example, a lot of the things that we take for granted in DMC, they just don't happen in AFQMC. Or, for example, if you want to start with a trial wave function for the excited state, and it is not particularly close to that excited state, you will actually decay to the ground state. There is nothing preventing you from decaying as it happens in DMC, where the nodal constraint simply is just incompatible with the ground state calculation. Another thing that's typical, if you're calculating a magnetic moment, an antiferromagnetic, for example, magnetic moment, and you initialize the system with a particular alignment of your moments, the constraint doesn't force you to remain there, and it would actually sample both configurations of your state. So you end up with a zero magnetization state, which it's the correct quantum solution. It's just particularly difficult to deal with if you want to actually get the broken symmetry average. Okay. So there's a lot to be learned, I should say, and we're trying to. So we're trying to gain experience. There are only so much work that has been done by the Shang group. Essentially, there's so much to be learned that I think with time we'll be able to get a better idea. But right now there's a lot of things that are up in the air.
I just wanted to confirm the VN here is the sampled operator that in the mean field subtraction. That VN is the operator you sampled.
So this would be the factorization. So when you have your two electron integrals, you have to rewrite them as the sum of perfect squares.
Yeah.
So the VN would be one of those. One term in that expansion.
Yeah.
So you would have to do this for each one of the n's. I will give you a particular form of that expansion in a few slides. There are multiple ways of doing this, but in all cases, it always looks like a sum over pieces squared.
Yeah.
And so each one of those pieces you would subtract independently.
Okay.
So so essentially we're going to do exactly the same as we do in DMC. We do importance sampling, which is you want to always bias your simulation towards spaces where the trial wave function has weight. And you do this because that's the best guess that you can come up with, essentially. And so you multiply by the overlap of the wave function where you end up, and you divide by the overlap of the wave function where you were. So that puts in your distribution now a term that accounts for the overlap of the state with respect to the trial wave function, which means that now before importance sampling, our wave function in the limit of large projection time would look like this. Now you have to unimportant sample the averages. This is not essential, but not essential that it's actually crucially important for the method as a whole. But anyway, so the propagation steps now looks like this. You have your Slater determinant, which is just some matrix. You are going to construct this B operator, which, as I showed before, is a product of essentially one body propagation, one body with the field, and then you do the one body operator again. These are essentially three applications of the exponential of a matrix, and that gives you a new matrix. And once you do importance sampling and force bias, you're going to end up with two pieces that I haven't said what, I just realized that I didn't say what force bias is. I'll go back to that. But essentially, you're going to carry these weights, which are just some scalar numbers, and represent the fluctuating weights of the water. There is a little bit of history being backwards here, by the way. If you look into the history of auxiliary field, the original formulation, you can show that in the small time step limit, this quantity becomes exactly the exponential of the local energy. So the original formulation of auxiliary field defined the weight as this. Sorry, it's missing the W. So the weight would be multiplied by this quantity. But this is only correct in the limit of small tau. And the reason why this was done is because this is the weight that you put in DMC. So essentially, originally, the algorithm was, Shiwei tried to get the algorithm as close as possible to DMC. Then eventually realized that calculating the local energy is quite expensive. And the only reason you need the local energy is to update the weight, whereas the original, which is the actual formal weight, without any approximation, does not involve the local energy and is way cheaper to evaluate. So he called this the hybrid method, but should have been really called the method, and this should be the local energy approximation, right? You can show that this has smaller fluctuations, but it's usually nowhere near enough to pay for the cost of calculating the local energy. So for big systems and in QMC pack, the default is just directly using the weight, and if you want the local energy, you have to say hybrid equals false. I mean, I'm pushing forward the convention, but anyway, it's important that it's actually quite cheap to evaluate. You only need an overlap, which allows you to do a lot of interesting things. Hopefully, I can go back to. I skip force bias. So the idea of force bias is very similar to importance sampling. When you're choosing these fields, importance sampling makes sure that if you end up in a place where the wave function doesn't have a good overlap with the trial state, your weight goes down and you can be removed from the population. But it does absolutely nothing to which state you end up in. Force bias is essentially when you choose a field, you can bias the choice of the field in such a way that you're pushed towards the trial wave function of the system. So that allows to, in the same way as doing force bias in DMC with the force, the force term in DMC pushes you to places where the trial wave function has high weight. Similarly, force bias would push you towards it would choose fields that push you in general towards the trial wave function, essentially. So it's simply a bias term, which it's at the end of the day, it's exact. It doesn't cost any approximation. just preferential sampling. And I will keep, there are many places where these averages come. So the mean field average of these operators are basically the average of each one of them with respect to the trial wave function. And in this case, the bias, what I call the bias potential, is simply the average of the same quantity, but using the mix estimator, the instantaneous mix estimator. So you have this later matrix of the Walker at one side and the trial wave function at the other. And the crucial point of this is that this gets to be adjusted to each Walker independently. So essentially, each Walker independently gets pushed a little bit towards the trial wave function.
What happens when that change signs?
What's the design sign?
Valuation.
And this ratio doesn't matter. It will matter on the overlap in one slide, and this is the cause of the sign problem. But this quantity in general, whether it changes sign or not, is not important. Well, it is important, sorry, but you don't need to do anything particular about it. You will end up taking the absolute value and keeping ahead of this whole thing anyway. And that's where the spaceless approximation comes. Is there any particular reason why you think this change in sign would be relevant?
You are getting something that is close to get very small. I was thinking that maybe there is a time step to worry.
Okay. So in all reason, when you have really large systems, you have to be careful about how you approach the limit where this becomes zero, because then these quantities can be large, and you have to be really careful. But it's more a technical discussion. I don't think it does anything to the formulation of the method as a whole. But it is something to worry to be honest. So the final slide about propagation now. So up to now, if you just do this, it will give you the exact answer with a really large error bar. It suffers from the sign problem in identical ways to DMC or to rotation or to any fermionic method that actually tries to solve the Schrödinger equation. And this is not the right way to derive it, but I don't have time, so this is sort of my cartoonish way of showing what happens. So, of course, because the fields are going to be always complex, the propagator, the two-body propagator always has this purely complex piece. Your walkers, your weights, are always going to be acquiring a phase. So if you let the simulation happen, there is nothing controlling this phase. It's essentially you're going to do a random walk where you're going to eventually populate the entire complex plane. So any quantity that you average over long enough time, you're going to end up with essentially the numerator and the denominator. They're both independently going to go to zero, and you're going to have the same problem. You have two small numbers whose ratio without error bars gives you the exact energy, but whose error bars are so large that the signal to noise ratio is just dying as you propagate things forward. So the solution is the same as real space DMC. Essentially, so in formal terms, you're projecting the wave function to the real axis based on this trial wave function. So you end up taking the absolute value of the correction term to the weights. That means that you're always going to end up with real weights. And so this averaging is stable and you don't have any problems with noise. In practice, you can think of this as you're applying fixed nodes, but in the space of slated determinants. There's going to be a trial wave function that's going to define, essentially, it's going to have some sort of nodes, and this is not going to allow your walker to cross nodes in this space. So instead of having a magnitude of a wave function as you walk in real space, you're walking in this later determinant space, and there's going to be a boundary set by when I have zero overlap with respect to a trial wave function. You can, all of the things that you can do in real space, you can show here too. If the trial wave function is exact, then this is going to have no effect, and you're going to have the exact result essentially. And there is a second piece that's more out of necessity, mainly. So you also multiply by the cosine of this piece, and typically what this does, this is not essential. You can run without this in some situations. But what this allows you to do is to make sure that you never really point where the overlap is actually zero. if you only do this, you can, in some sense, walk around the complex plane and always get fairly close to the divergence when this becomes zero, and that would unstabilize the algorithm. So essentially, you put this term in here to kill walkers that get a little bit too close to having an exact zero overlap. But for many systems, this is actually not essential. Okay, what about observables? There are, as I mentioned, two ways of getting observables. You can do the mixed distribution. This would be quadratic in the quality of the trial-wave function. This is a little bit of a cartoonish way of saying quality of the trial-wave function. So the better the trial-wave function, of course, in the limit of an exact trial-wave function, you have zero error. But whether that error is linear or quadratic on the error, on the difference between the trial-wave function and the exact eigenstate, matters a lot to observables. If you calculate the energy is amazing because it's Hermitian, and essentially you can show that because it commutes with propagation, essentially, your error will be quadratic on this difference. So even though your trial-wave function is not perfect, it's not great necessarily, you actually have an energy that's pretty close to the real answer.
So is there a property like nodal structure in DMC that you can gauge the accuracy of the trial-wave function?
So yes, I would say yes and no. So yes to the term that there is such a thing would be the place where if you take some arbitrary matrix, it's where that matrix or a walker with an arbitrary representation is where the overlap of that walker and the trial-wave function becomes zero. That becomes your nodal surface. And I'm going to say no in the sense that I guess I don't like the premise. I don't think you can conceptually think about nodal surfaces, but they're not really practical. I don't think that in DMC we can actually say this nodal surface, just push it back a little bit and you'll be better, right? So we have a philosophical way of understanding the approximation that we're making, but it's really not practical in that sense. So in the same spirit, you can understand what the method is doing and what the constraint is doing, but you have no practical way of making use of it. So you cannot really.
So could I sort of generalize or restate the question slightly? So in fixed node diffusion Monte Carlo, and of course in variable Monte Carlo, right, we're used to using the variational principle on the energy to gauge the accuracy of the wave, or to gauge if we made an improvement in the wave function, right, at least. So lower energy, also less variance is better. What can we look at in auxiliary field to give us a hint on how we're doing?
That's a great question, one that I completely forgot to address. So the auxiliary field method is not variational. So, and I guess this is the perfect place to say that. So because we are projecting on a subspace, essentially, this is not a variation. This does not guarantee a variational quantity. So you can easily get results that are below the exact energy. There are many different opinions about this, and usually this is discussed heavily on the quantum chemistry community. For example, coupled cluster is not variational, but it's typically a very accurate answer. So you don't need variation of it. You don't need your answer to be variational to be accurate. And some people would argue that coupled cluster is accurate precisely because it is not variational. But anyway, the short answer is it is not variational. So you need to find an alternate way to understand the quality of the calculation. So just looking at the energy, it's not that it's irrelevant, but you cannot just walk down towards the minimum. So the variance is a meaningful quantity. So in our experience, we still don't know exactly how to minimize mathematically the variance, but we can do things that are close enough to minimizing the variance. And typically, low variance will mean better calculations. That means smaller fluctuations. That means that you're closer to your eigenstates.
So Miguel, for example, if you remember, I don't know if you're paying attention, but I showed a curve with multiple functionals that I started with. If you were to do the same thing at the AFQMC and take B3 PB0, it starts from those as trial-wave function, would you find something sensitive that you can say they will lead to the same answer at the AFQMC level, or you would still see the same type of shift that you see?
So he's asking if I do what he presented about taking different DFT waveforms, for example, and then looking at the results. So I guess I also don't accept your premise. So this is very system dependent, right? I can give you a system where Hartree-Fock is the best wave function, right?
Yeah, but
So, but the one thing that I haven't done, and so I don't have it to show here, is if I take a bunch of molecules, for example, and I look at the variance of the energy as a function of the error that you're making. What should happen is that the smaller the variance, the closer the energy is to the right answer. I think that this is correct. I haven't done it, so okay, let's just say that this is an exercise for us to do, but I strongly believe that this is the case. And in the few cases where I actually have done this, right, in most, what will tend to happen with AFQMC is that it is typically, for single reference systems, it's so good that you really don't need to think too much about the wave function. So for most molecules, your errors are fairly small, and so it depends on what quality you want. Typically, it doesn't take that much to fix them. You have to go to fairly complicated correlated systems, and there you will see sensitivity to the tri-wave function. I've been spending quite a bit of time looking at solid nickel oxide, and there the influence of the tri-wave function is large. You can make 20, 30 millihartree errors by changing the wave function. The physics is hard because you change the wave function and you're changing the oxidation state of the nickel. So you're moving one electron away from nickel and to the oxygen. So there is a reason why that sensitivity is there. We're still not at a point where we can absolutely find the perfect wave function through direct force. We still need a little bit of intuition and maybe a little bit of external help. We have ways of improving the wave function, but essentially for a big system with like 100 atoms, we still don't have that clear path towards improvement. I should say that AFQMC is quite young, doesn't have so many years, so ideally this gets improved over time. But right now there is nothing that I can say this is exactly what you do and you get the perfect wave function.
Is it easier to compute the overlap matrix between the trial wave function and the projected wave function in AFQMC than in real space projected?
So no, so he asks, and correct me if I'm wrong. So if you want to calculate the overlap between the trial wave function and the projected trial wave and the projected state, so that would be the normalization of your distribution. It is as hard as calculating a free energy. So it's hard. I mean, there are ways of doing it. You can do lambda integration, for example, where you switch the potential and things like that. But in general, calculating that overlap is difficult. It's what you're sampling on. So essentially, it's the same as calculating a free energy, which is really hard. Yeah.
We have heard a lot of the importance of CASP conditions in DMC. And here in auxiliary thinking, we just move the single particle orbital without caring about the CASP condition.
So when I get to the next slide, that's going to be one of the. I'll get back to that. So, well, anyway, I can say right now. So he asks, in real space, we're always worrying about cusps and about divergences and about things that become infinite. Auxiliary field doesn't have that because your basis screens out and regularizes any interaction. So even though electron-electron is 1/r, it's really it's what the matrix element looks like. And the fact that we use basis sets that are Gaussians and fairly smooth, we don't see divergences and we don't have those problems in AFQMC. If you want to recover the electron-electron cusp energy, that requires a very slow convergence with respect to basis set. So you get to simplify the problem in a sense by putting a basis, but if you really, really want the cusp energy, then you have to put a lot of work in recovering it. It's a little bit of a trading game. And so you get to choose what you want to do, what's more important to you. And I'll get back to that in a slide. But essentially, nothing diverges here, other than possibly the inverse of the overlap with respect to the trial wave function. And so the mixed distribution, essentially, we take any observable and we calculate the mixed matrix element with respect to the trial wave function and the auxiliary field on the other side. Not really going to go into details, but the idea is that if your operator commutes with the Hamiltonian, this is converging quadratically. If it doesn't commute with the Hamiltonian, for example, the force or anything else that you might want to calculate, almost everything doesn't commute with the Hamiltonian, your operator is going to actually converge, your average is going to converge linearly, so you're going to see a lot more error and a lot more sensitivity to the trial wave function. So you have only two paths forward. You either really improve the travel function if you can, or you use what's called backpropagation. Backpropagation is very simple in nature, right? So I projected my right-hand state, so just project the left-hand side state too. This requires in practice some care in formulation. This is not as naive as just take any two random walkers and do the overlap, because if you do that naively, your computation is going to be quadratic on the number of walkers, which is going to explode. So the whole point is, how do you formulate this in such a way that the cost is still linear in the number of walkers, but you get well projected states on the right and the left-hand side. And as always, I'm really not going to go into detail. There are some really good papers. There's one particularly good paper in the set of papers that I gave you that describes how you do this, and it's very nice and a well-contained paper. But the idea is essentially that now we are projecting left and right, and so all operators are now guaranteed to converge quadratically with respect to the quality of the traway function. That doesn't say that the bias is going to be removed. It just means that if you were to do the hypothetical example of somehow varying the quality of the traway function and looking at the error, that should go to zero quadratically. In practice, it means much better observables. So like densities and moments and things like that, forces should converge much better. It's typically, so as of the last version, I'm pretty sure I pushed last week. So we rewrote recently our backpropagation scheme, and now it only takes somewhere between 50 to 70% overhead with respect to a calculation that doesn't have backpropagation. There is a little bit of a price to pay, but if you think about it, you're really doing two calculations. You're essentially projecting twice. So,
That's a question.
Sorry.
So you might come to this later, but is there a lot of memory costs to that?
There used to be, not anymore. So that's the main reason we rewrote it, is because it was the previous implementation was really memory intensive, for too memory intensive for the GPU. So we essentially redesigned it in such a way that we use as little memory as possible. We have to recompute more things, and whether the new implementation is better than the old depends on what is expensive. For bigger systems, the actual propagation is what consumes all the time. So. And in GPUs, which is where basically all the computing power is these days, low memory definitely wins. So there is some extra memory, but it's not dramatic. It's 10, 20%, something like that. So just to set a point, a flag, for example, when I do the magnetic moment calculations in Nickelotsa, we're doing backpropagation. We have to backpropagate thousands of steps because antiferromagnetism decays really slow. And we are doing this on systems with 108 atoms. So this is roughly the scale. We can probably do even bigger, but this is at the scale of what we do routinely these days. Okay, so what time is it? So let me spend the last 10 minutes talking about sort of trying to get a feel between the auxiliary field and DMC. And so, of course, I like the auxiliary field because it's new, it's exciting, a lot of things are happening, but it's not the method for every problem, absolutely. So let me start by so blue is good, red is bad, actually. So what is auxiliary field has one of the things that I like the most is that it has a very direct connection between model Hamiltonians and ab initio, because it lives on a basis. You can almost draw a line between a Hubbard model and the real Hamiltonian for whatever system you want in real life, right? So you get to simplify. It gives you a natural way of obtaining a simpler problem that maybe you can tackle better, or maybe you can focus on different physics. But it also has the complexity to give you the full basis converged result, right? So you, as a user, get to more or less decide where along the line you want to solve your problem, where you want to focus your attention. And there's a big community in how to generate accurate model Hamiltonians that we haven't overlapped too much with them, but I think there's a lot of fruitful work that could be done but try to walk a little bit better this path between ab initio and model Hamiltonians. It's very flexible on the treatment of core electrons. This is one of the reasons why I started doing this. In Livermore, they really care about heavy elements. So because all the work gets done at the mean field level, and auxiliary field really doesn't even know what an orbital is in practice or where it comes from, you just need matrix elements of the one-body Hamiltonian, and that one-body Hamiltonian can be anything, and the basis set can be also anything. So you get to choose what you want to do. You can do all electron, you can do frozen core, you can do ECP, LAPW. It really doesn't matter. It's going to be a matrix that AFQMC reads at the end of the day. You can do spin orbit fairly easily. So as I will go at the end of the talk, at some point in the next, I would say 6 months or so, we're going to have full non-collinear AFQMC with spin orbit coupling. And it's very straightforward, essentially, to do. The changes to the algorithm are minimal. Essentially, the only change is that now a Walker would have a Slater matrix for up and a Slater matrix for down. In non-collinear cases, one big Slater matrix that has both up and down components. And that's it. Your one-body Hamiltonian now has off-diagonal spin components, and that's it. Everything else follows identically. So this is, take it for what it's worth. I would say that in general, we have seen smaller biases in AFQMC compared to DMC, but that has to be taken with a grain of salt, and I'll go back to that in the next slide. And the other thing that we love is that it's really efficient. It's all, if you have BLAS and LAPAC, you have 95% of what you need to write an accelerated control. So in GPUs, this is perfect. One of the negative sides is that it's a very small ab initio community. So up to before we started doing this, there was one group of Xu Shang essentially doing all the work. They have been doing this for some 15, 20 years. They have a lot of work that they have been able to do, but it's still a very small community. No community available codes. Essentially, you would have to write your code from scratch. And the main point of what we're trying to do is to put forward that community code so that maybe people start to use it and the community grows. Of course, the really elephant in the room is that you put a basis, so you have to deal with basis at error. This is by far the largest problem. So if your mentality is the CBS limit, and this is really what you care for, then of course this side of the comparison is going to be better for you. And you need to put work at getting to the CBS limit. We really, if you quantum chemists have spent their entire, this is where they live in finite basis, so they have a massive amount of wealth of exactly where that error is and how to get it back. It usually takes quite a bit of computation to compute that, but there are well-defined ways. And they could all be done on top of AFQMC, like F12 or transcorrelated.
Yeah, but that applies really mainly to the molecules, namely systems in vacuum. If you start to talk about solid periodic boundary conditions, conduction state, and all that stuff, there is much less obvious how the cancellation of errors with the basis goes.
I would argue that is going to change, and I would argue that it's very transparent when you go from one page to the next. The problem is that there is as little of a community of AFQMC is. It's even probably as small the periodic, ab initio community in quantum chemistry. But if you look at the work of Andreas Groneis, he has a paper out in March where he really shows when you do periodic coupled cluster, he can really quantify exactly where the basis of error is coming, and it's coming from a very particular from two diagrams on the expansion. So I think 3 or 4 years from now, it's really going to move forward the field, and we can just get on that bus and ride around with it essentially. But what I'm trying to say is that even though the basis set error is large, I think my personal opinion is that it's trivially large in the sense that it's universal quantum mechanics. There's nothing, most of the basis set error is from a cost condition who's universal. You don't really need to know that much of a system to get a really good idea of what that quantity is. So I think it's easier, in my personal opinion, to find a way to correct for the basis set than it is to reduce the fixed node error. Anyway, you had another question?
No, okay. Go ahead.
And so the other Achilles heel was essentially you have to deal with this n to the fourth quantity. So a few years ago, you start building the code from zero, we just would store an n to the fourth tensor. And of course, that limits tremendously what you can do. That if you were to do this like that, you would limit your calculation to tens of atoms at most, and even that would be expensive. So we have spent most of our mental juice and our time in essentially trying to fix this problem, where the memory is really not the limitation anymore, and we can actually move to the more harder problem, which is improving wave function. So the reason I crossed this out is because this slide would say, m to the fourth memory cost. Now we have methods that allow us to do formulations that are quadratic or cubic in the memory. And cubic, we can handle. Quadratic, we're basically done. We don't need to do anything else. And we have those implemented in the method. There's a lot of caveats, and I'm going to get to those in the second half hour. But essentially, we consider the memory problem gone. We can do 200 atoms, and that for us is good enough. The final thing, which I added just this morning, is that forces are particularly hard because they are easy to get. They require a lot of memory because you don't only need the two electron integrals, you need the gradient of them with respect to all particles in the position. So the memory cost of forces is huge, and that's our next frontier. Ideally, in 2 or 3 versions of this, I get to write this off. But right now, the main problem with forces is really the memory consumption. So on the DMC side, the best thing that DMC has is that it's explicitly correlated. You put a Jaster for free, and you essentially get really close to the many-body state. There is no basis at error, so you're basically already at the CVS limit. As Anwar has shown multiple times, that's not quite true with respect to the trial wave function, but in principle, if you get a good enough trial wave function, you are at the CVS limit. It's very memory friendly, 3 n numbers per walker. I have a huge matrix that I need to store, and it's very intuitive. In the same way, you can talk about it, and you can, with your hands, you can sort of explain what's happening. AFQMC is working on this mysterious space of non-orthogonal slated determinants, and it's a little bit harder. So, on the negative side, DMC, in my opinion, is really hard to simplify. So you have the many-body Hamiltonian. You might get to soften the potential, and that's it. So you don't get anywhere close to or to remove irrelevant degrees of freedom, it's really hard to even do frozen core, for example, in real space. So if you have a spectrum between model and reality, you are here, and that's it. You either solve the full problem or you don't. And I find that, in many ways to be a limitation. It has uncontrolled approximations, what's called the locality approximation, which you might know or you might hear about. Essentially, if your pseudopotential has non-local channels, that's an approximation that you cannot do much about. And none of these approximations are in AFQMC, so it's still unclear, essentially, where this falls in the line of importance. The one thing that's really clear is that if you're not careful building your pseudopotentials, these would be orders of magnitude larger than fixed node. So the first time that we naively tried to do heavy transition metals, we just grabbed the FT potentials, and it was a massive disaster because this error was 100 times larger than the fixed node error.
That's just the lack of experience.
Of course, yeah. We just said, okay, do it. Get opium, get a pseudopotential.
Oh, I see. Right? Wow, with opium route, I mean.
But what I'm trying to say is that
it should be called heroin. It's
But what I'm trying to say is that it's there, right? You have to realize that it's there.
Be trained exactly as you have to be trained in basics.
Right. So the fixed node error also can potentially be large. So this should be more like orange, and this should be like very, very light blue, because we don't really understand very well where that balance is. But in my experience, the fixed node error is larger, mainly because you have a divergent potential. So if you make a small error in your node very close to the nuclei, this would shoot up some large errors, right? So, and we sort of screen that with a small basis. If we were to do a ginormous basis, we might maybe see similar things, although in practice, I don't think we do. The other thing is that spin orbit is non-trivial, at least to me. I know Lewis doesn't.
I'll try to.
So he's going to talk about that.
More trivially than.
At least right now, it would take me, a couple of days to get auxiliary field to do spin orbit. I think it would take me a lot of thinking and to get in DMC. So maybe 5 years from now, things are different. When I wrote this, which was...
You will see that the way how the spin orbit is treated is actually a little bit pushing DMC towards AFQMC, because you have a subspace on which you are doing actually AFQMC and a big space on which you are doing DMC, and I claim that it's the sweet spot between those. But anyway.
Okay, so this might completely go away. So. And the other thing, which is your point, you have divergent potential. So, I mean, when you reach expertise and when you have really fine-tuned codes, all of these things have been worked on, but, it took 20 years to get to the point where we can say, you don't need to worry about these things. It is still something that if you make a very tiny error, it's going to propagate and it's going to become pretty large. So the last slide before we take a break.
May I ask you a question before the last slide? You have to decouple the V's that make it into single square operator potentials. You basically have to diagonalize that big matrix. How much is it?
No, so you don't. So if you can do it. So his question is, if you have the four index tensor, and you want to recast that as a sum of squares, you have to diagonalize the matrix. So that is the naive, that's what I call the naive way of doing it. If you do that, you still have years to go before you actually get to the point. We can do this essentially with very little cost. You can do Cholesky decomposition, for example, or you can almost directly, if you have K-point symmetry, essentially this drops out. There is some setup that will be expensive, and I will talk about that, but it's not that. This is really not the issue right now. Essentially, you just go and read what quantum chemists are doing. You do it for solids. Okay. They have been fighting this for 30 years, right? So actually, more. They revolutionized how they do this in early 2000s with density fitting and things like that. So it's already noon. I can continue, or you tell me. Right, so the next slide is about the code. So this is the last slide, which is...
Okay, so do this one.
So I'm just going to do this one. So this is and please, this is for illustration purposes only. Don't take too much out of it. I don't really know how much this holds, but we did one example where we compared DMC and AFQMC. We took a 2-atom-unit cell of carbon in the diamond structure at equilibrium. This is a very simple calculation. So we took a small basis, we took multiple bases, but it's so small, it's only 2 atoms, that you can actually do selected CI, which is we're not talking about this here, but it's a powerful way of doing stochastic configuration interaction. And you can actually extrapolate in such a way that you get a very good idea of what the exact energy is of this unit cell. So it is this cartoonish small, but we can really hit it hard and see what's happening.
Results are correct. This holds.
Right, but I'm saying if you change the system, right, then we don't know what's happening, right? But for this particular case, and I have to say, carbon is particularly simple. So any paper that you see with carbon, really don't take it too seriously. It is really nice from the point of view of fixed node error and faceless error. So in blue you have DMC, in red you have AFQMC, and you cannot really see it, but hopefully you can see it better in your slides. The bright part of the bar represents single determinant results. The darker part of the line represents converged multi-determinants. So that means in DMC, millions of determinants until you see the error doesn't change it anymore. And in AFQMC would typically mean a few hundred determinants until we're converged. And what we're plotting is the percentage of the correlation energy that you're recovering. And so what you can see, and you have different basis sets, double, triple, quadruple, and double, triple, quadruple, and the basis set extrapolation. So there are two salient features. The first thing that you see is that you're getting very close to 80% of the correlation energy regardless of the basis set in DMC. That's good because it's not so sensitive to basis set, but it also means that you have a 20% fixed node error in your results. On the AFQMC side, you can see that the darker part is very small. We're getting somewhere like 5 to 7 millihartz errors whenever we do single determinant. So the capacity to solve the problem for that particular basis is really high. Your faceless approximation is small. But if you want to recover the total energy in the CBS limit, you really have to work hard for different bases. So you're trading 20% of fixed node error for the necessity of doing basis set extrapolation. And so this is mainly the middle of the ground in this, right? So which side of the coin do you want? I'm gonna be careful not to say anything too strong, but because this is the AFQMC talk, I'm gonna say it. So the whole point is that, right? If I were to do some rough method, something like MP2, and I would ask MP2, what do you think is the basis of correction? And I would put it on top of these results, I would be up here, right? My error would be very small. And even some theory like MP2, which is very cheap and fairly simple, it already gives you a very qualitative idea of what basis set error is, mainly because the error is coming from the electronic cusp, and the electronic cusp, I need to keep saying, is independent of system, it's universal. What the wave function looks like near the cusp, it's universal for any system, essentially. So as long as you have enough correlation in your approximate method, you're gonna get a reasonable idea of what that's cusp correction is. So in my opinion, you're trading something that is more universal and easier to extrapolate, but it might be very large in magnitude. So you have to be careful. On this side, you are at the basis set limit, but it's not entirely trivial to remove the fixed node error, essentially. So I think this might or might not hold in general. I think it is, it gives you a good flavor of exactly what the comparison between the two is. And I'm over by 5 minutes, so I'm going to stop here.